So I'm going to hand out the last project is Thursday, which is gonna be due somehow middle of March. That's gonna be the last project. And the project is gonna be not assigned problem like your first project. First project, I gave you equation and boundary condition, and you have to write a program to solve it. This is gonna be the term project. So you decide what kind of problem you're gonna work on, okay? And then you are going to uh, solve that problem and provide me the report. Okay, of course, the one of the minimum is that you have to use a finite technique because that's the FEM class itself. So you have to use the finite class so that you have an option. You can write a code yourself like your first project, or if you want to use some commercial program or some other program, you have ANSYS and also a couple different program, and you are going to use that program to more realistic problem, then you can do that too. So you have an option, and also you may work as a team. In other words, that I'm going to work with this lady or this gentleman to some common interest, then you are welcome to do that. Of course, if you work as a team, then the scope has to be a little bit broader than just individual project because the two people have to work together. So anyhow, the bottom line is it's more flexible, and then that's going to be also one of the way you can learn and appreciate the finite solution technique for diverse problem, not just single textbook type of problem, but different problem. So one of the best way is, especially folks in here, that you are working on your thesis, right? So if you can relate your project to your thesis topic, that would be great. If you don't have any thesis topic, that's fine too. But somebody who is already working on thesis, then something you can solve that using your FM program, why not? So you can kill two birds with one stone. So that's going to be another opportunity for you. But it's all up to you. I'm not dictating anything. So I'm going to hand it out that the project assignment this Thursday. Then you can read it, and also we can discuss more about that. All right. And then also this Thursday we'll talk about the schedule for the final exam. So we are going to finish class a little early. So by early of the March, so you have some time to work on your project and also prepare for the final. So we'll talk about the final. The schedule is going to be like the take-home exam, like the midterm exam. Okay, but it's going to be comprehensive from first chapter to the last chapter we are going to complete in our class. So we'll talk about that more next time. And now I'm going to go over briefly the exam problem. So most of you did very well, but again, some people who missed a couple of the concept, then I hope this is going to be an opportunity to learn that. So I'm going to go over briefly, and I gave you that my solution, and most people pick it up, but some people didn't pick it up. Maybe you already got the right answer, so you may not need that solution. That's fine too. But anyhow, so I'm going to go over that briefly here. You can see it, right? And of course, you have seen this problem too. So you have a piecewise solution. Of course, in this case, not linear. I give you some quadratic function. The reason is that should be you can take a derivative, second derivative in the least square method. So idea is that here, maybe I can use, if you can look at this solution, can you read it? Maybe to let me somehow close up. Can you read better? Can you dim down the light a little bit? So, especially the front side. Better? Okay. All right. So then this piecewise solution is going to be expressed again piecewise from 0 to 1 and 1 and 2, like that one. Okay, this is nothing but this expression. And then the main thing is going to be right now, this is just normalized one, okay, when you assume this solution. And then we are trying to find what is the actual magnitude of this solution so that it's going to be multiplied by A. So A is going to be common between this section and that section. Some people make a mistake that this is going to be A and this is B, and that's not the case. That means A and B different. That means it's not going to be continuous function. It's going to, one solution is like that, the other solution will be like that. And so we have discontinuity at that one. So it's going to be a single parameter, A or B, whatever C you want to use, but one parameter for both sides. So that indicates the magnitude solution. So it's going to be A is going to be larger than one, then it's going to be something like that. Your solution is going to be looks like this, okay? Then you have to calculate residual. Again, residual is going to be between 0 to 1 and 1 and 2 because you got piecewise solution. And then take a derivative with respect to A, that's the least square method. So then you got this, test function. And another, few mistake is that now the integral of the whole domain is equal to 0. In other words, from 0 to 2. Of course, you cannot integrate with a single function from 0 to 2, so you have to break down into 0 to 1 and 1 and 2, but that's going to be just one equation. So one equation for one unknown A, so you find the A, okay? So again, not many people, a few people made mistake that A and B, and then you said that integration of the weight residual from 0 to 1 equals 0, and then 1 to 2 equals 0. So you got two equations, two unknown, find A and B, but that's not the case. That means your solution is not going to be continuous within the domain. So that's the first part. And second part of the exam, this one is basically same as your project. So I want to, test you out that whether you understood the project and did that properly. Of course, I trust you, but if you really didn't do by yourself, and then you got some help from your colleague and work it out and you don't know what to do, that then you're going to stuck in this problem. So, I mean, this is to make sure you really understood that convection type heat transfer, so that this is going to be the main problem in here, convection type. So convection type is going to give you both that the mass matrix, I mean, not mass, sorry, that the matrix and column vector. So it gives you this one and column vector, okay? So that have to be added to here and then add to here and applying bound condition. So applying bound condition is one also small mistake people have done is when you have this U1, U2, U3, and then F1, F2, F3. Can you read it? And then you got, 3 by 3 matrix. So U1 equal 20, then yes, that's going to be 20, but you cannot just leave it 20, then that's not proper, because that when you say 20, that means this is going to be 1, 0, 0. So U1 is going to be actually, this is going to be 20. That means the U1 is going to be 20. That's what you have to modify the equation to make it U1 equal 20. Okay, so that's the proper modification of the matrix equation to apply U1 equal 20 in here. So 1, 0, 0, 20, and elevate this one U1 is going to be, the right way to write a matrix for U1 equal 20. Anyhow, so main thing is going to be this matrix and column vector. So as I mentioned, that this is the two-dimensional problem. So domain is two-dimensional problem. So whenever you do the boundary integral, so in this equation, when you have a boundary integral term, then boundary is going to be 1D shape function. So you have to use 1D shape function. That means you are going to have 2 by 2 matrix and 2 by 1 column vector from there. And if you extend it to 3D, so if you have some hot potato shape, this, let's say this 3D, and then if I use tetrahedral, then surface is going to be like a two-dimensional, triangular element. Then you are going to have a 3 by 3 matrix for that the surface, and inside, because inside is going to be tetrahedral, you are going to have a 4 by 4 matrix for that one. So again, that's the difference between domain integral and boundary integral. Okay, so boundary integral is going to be always one-dimensional less in shape function than domain integral. And the third one is most of you, again, to follow properly, and then also many of you did the right thing. But main thing is now we want to evaluate this one at that point. Okay, x equals 0, y equals 0 in here. But this is going to be using isoparametric, bilinear isoparametric element. So in other words, this is the derivative with respect to c and eta. So the main thing is now from this equation in here, x is, if I rewrite here, make it a little bit bigger. X is summation of hi xi, right? So of course here, hi is going to be c and eta, and xi. Y is also summation of hi, c and eta, and yi. So we know xi, yi from this geometry. 1, 2, 3, 4, or 1, 2, 3, 4 in given 1, 2, 3, 4. And then if this is equal to 0 and this is equal to 0, which is going to be the location in the physical coordinate system, then by solving this equation, you are going to find c and eta, and which is not that difficult to find it. So you got two, c and eta, one is going to be positive, one is going to be negative. Then after you do all the derivative, just plugging the c and eta. That's all you have to do. And the last one is to find that, distribution of the flux at the boundary. But the key is, okay, using isoparametric element. Okay, isoparametric element. So if you use conventional element, yes, you'll get the exactly same answer. But the question is whether you can apply the isoparametric element. So if you did not isoparametric element, then definitely I subtract some of your, the point there. So again, main thing is going to be, in boundary, whether, excuse me, let's say, this is the geometry of your body, right? So those are the boundary. And the simplest way is that you just give every boundary the new coordinate system, let's say not xy, because xy is going to be given this way, right? So let's say s. Then this is s, or you may say this is also s, and this is s, or this is s. You can do whatever you want to say, just using new, s itself. This is going to be dummy, coordinate, so it doesn't matter. Then you have a shape function, for example, h1 and h2 in terms of s, right? And then using the isoparametric element, you are going to have a mapping between your coordinate system in the isoparametric coordinate system, natural coordinate system C, and then the physical coordinate system S. So once you do that, then you can see that your S is going to be 1 plus C, and then the integral is going to be integral W du dn d gamma, right? So du dn is going to be shown in this one. So W is going to be the test function. So if you use isoparametric element, there's the W1 and W2, and that's going to be du dn in terms of C. And of course, then this is going to be mapped into that the natural coordinate system, the Jacobian, and then you got the same answer as you used to get from the conventional element. So in this case, obviously, if you use conventional element, it's much easier to get the same answer. But I would just want to practice the isoparametric element because that's typically the formulation in virtually every FEM program. They never use conventional element in general because you cannot write a general purpose program using that one. So anyhow, that's the key in the last problem in here. And if you have any further question about the problem and solution, then you are welcome to also ask me. I'll be happy to discuss with you also after class or any other time if you are going to make an appointment. All right, so that's for the exam. And any questions so far? All right, then let's continue the discussion we did last week. So we studied theoretical elasticity. Again, we spent quite a time because we never learned theoretical elasticity in any other classes. So this is the first time you learn this one. That's why I have to give some extra, the lecture for basic of theoretical elasticity, not just finite formulation, but concept of theoretical elasticity. So theoretical elasticity is that we are going to satisfy equation equilibrium every single material point, not just average sense, but every single material point. So your differential equation is expressed for equation of equilibrium. So equation of equilibrium is in terms of differential equation, which is very different from the standard mechanics of material approach, which is going to be algebraic equation of sum of force and sum of moment. But now this is in terms of stress because you have to satisfy that on every location. And you got the stress matrix, or we call stress tensor. I don't know if you heard about tensor, okay, mathematically stress tensor. So tensor is more general than the matrix itself. In other words, tensor, we use notation, any symbol, let's say sigma is going to be the symbol we are going to use, then we use index here, all right? So if you don't have any index, just sigma, let's say, then this is going to be a scalar quantity. So zeros order tensor. There's no direction. And if I use sigma I, so for example, sigma x, sigma y, or sigma z, okay, if I use single, then that's going to be first order tensor, which like a vector. Vector has x, y, z component. This says first order tensor. And then if you have ij, two indices, then that's going to be the matrix like this. Depending on ij, it's going to be 2D matrix like that one, like a sigma 1, 1, or xx, sigma 1, 2, sigma 1, 3. If I use 1, 2, 3 notation instead of x, y, z, 2, 1, sigma 2, 2, sigma 2, 3, sigma 3, 1, sigma 3, 2, sigma 3, 3. Okay, so this is going to be second order tensor. And then if you have another index, then third order tensor, fourth order tensor. So in other words, the scalar, vector, matrix are one of special cases of tensor. So tensor is more general, okay, term for those kind of nature. So this we call second order tensor, which is going to be like a matrix in here. And then we introduce the constitutive equation. And the constitutive equation is going to be the relation between stress and strain. And from isoparametric, I'm not isoparametric, isotropic material, transversely isotropic, orthotropic, and the most anisotropic material. We talk about those kind of, transition. So most complex problem is going to be anisotropic. but that one you have, for example, 21 material constant, virtually impossible to determine those constants. So normally we never model anything assume generally anisotropic because of the complexity of getting all the material. So usually isotropic or orthotropic. Okay, those are the most engineering material we deal with. And isotropic is the simplest one, and we need just two material constant. And then starting from 3D, we talk about 2D, plane stress and plane strain. And they are very similar, but slightly different. I said the difference is about 10% as long as parts ratio is going to be 0.3 around that value. So that's we talk about it. And then the last set of equation was kinematic equation. So kinematic equation is going to be the strain displacement relationship. So in other words, how do you measure strain? So in simple way, we use that, delta U over delta L. Length change per, the initial L, original length. That was that kind of average strain. But now strain is going to vary from point to point like a stress in more precise manner. So you have to express the strain in terms of du dx. So small change of displacement for small length, original length. So this is going to be more localized, point-wise definition. So you have a two normal strain and one shear strain for 2D, and 3D you have a three normal stress strain and three normal, three shear strain in here. Okay, and if you are going to do some also stress analysis, then you may hear a little bit unique term that so-called engineering shear strain. Okay, and tensorial shear strain. So they differentiate between engineering shear strain and tensorial shear strain. The difference is those are engineering shear strain. Those are engineering shear strain. Then what is tensorial? Tensorial shear strain is, for example, gamma xy is not just du dy plus dv dx, but it is divided by 2. Okay, so when you divide this by 2, that is called tensorial shear strain. Same thing for this one. If you that divide by 2 and this divide by 2, that means those are tensorial shear strain, xg and yz, like that. Okay, and I'm not going to talk about the detail why they have to separate this one, but in a simple sense, this is good for engineering concept. Makes much more sense, and this is useful for mathematical formulation because this one doesn't work in terms of mathematical formulation. So they, define a little different shear strain so that they can do more mathematics easily. Then when this is going to, why this is important. So depending on how you define the shear strain, okay, the difference is going to be this one, right? So D is going to be the relationship between stress and strain. So stress, just simple, single definition, nothing, different between tensor and engineering, just one value. But depends on how you define that one. This is for engineering shear strain. So this is for engineering shear strain. But this is defined, this is used for tensorial shear strain. Then what? This have to be multiplied by 2 because 1/2 is divided by, applied in here. So this is going to be multiplied by 2. So depending on what kind of shear strain component, your quantification is going to be slightly different, right? So whenever you look at the shear strain, you need to double check whether this is going to be engineering or tensorial shear strain. Again, the difference is going to be 1/2 or without 1/2. Okay. And then boundary condition, we talk about two different set of boundary condition. Essential boundary condition, for example, displacement is given. So we call geometric boundary condition. And then the other is going to be the traction boundary condition. So load are applied, like the pressure loading is applied. So we also call static boundary condition for data. So we have two types of boundary condition. And then the boundary traction. So traction is like a stress, but over the surface. Boundary surface, we call the traction. The same unit as stress, but you give a little special name. And then, so once you have this, proper boundary condition in here, then everything is ready to be solved. So you have a 3 set of equation of equilibrium, constitutive equation, kinematic equation, and then proper set of boundary condition. Then we are ready to solve that. So today we are going to talk about now final element formulation of zero velocity, how you do that. You have a 3 set of equation. So the way we are going to do it, we are going to start with equation of equilibrium. Okay, equation of equilibrium. So we are going to apply method of weight rigidity to equation of equilibrium. So this plus this is body force. This plus this body force equals 0. So multiply by W1 and W2. W1 and W2 both are domain integral. And you don't have to worry about this one right now. So let's say ignore that. So we start with your equation of equilibrium. And if you don't have any body force, such as your gravitational force or centrifugal force is not that important in the problem, then you ignore this one. Okay, so this is like in heat transfer, heat sink or heat source. But heat sink, heat source are scalar quantity, but this one is vector quantity because you have a body force x direction or y direction. If this is going to be 3D, you may have that in the g direction too. So starting with that, so that's going to be the starting point for the method weight to be there for zero velocity. Then what is the next step in here? And if you look at this, here, if you stop here, unfortunately, we can do much about it. We are going to stop at this point. So we have to do some mathematics. So what we are going to do here is we are going to apply like a weak formulation. But this is slightly different from the weak formulation we talked about previously. Previously, when you say weak formulation, for example, this is the test function, and this is the trial function, then we want to make the burden means the derivative, as close as possible. So in other words, this is going to be 0 and first order, that's the closest one. And 1 is going to be second order, 0, like a second order differential equation. Then we apply weak formulation, so first order, so you want to make it that equal or as close as possible. So in this case, this is 0, this is the first order, so that's the closest, indifference between derivative of test function and this trial function. But in this case, we are going to apply integration by part of those every single term, this term and this product term, this term and that, every single term. Why? I'm going to explain that in a minute. So first of all, how do you apply integration by part? If you remember what we did in chapter 5, we developed that equation. Can you make it a little bit brighter? A little bit difficult for me to see, a little dark. So yeah, a little bit. Yeah, not, oh, yes. Yeah. Is that okay? So in here, now the this equation, we are going to apply integration by part here. So we are going to do term by term. This term and this term, and that term. So if you do integration by part of this one like x, then what? This and that is going to be reversed. So that this is going to be dw1 dx, and that's going to be sigma x. Okay. So p q prime, then that's going to be q and p prime. And then this is going to be now the bound integral is going to be p and q. So w1 sigma. Okay, that's going to be integration by part in 1D problem. But this is not 1D, multidimensional case. So it's not going to stop in here. If you remember what we did in chapter 5, we are going to have normal vector. So if this is going to be integration by part for x direction, then this have to be multiplied by n sub x normal vector along the x direction. Okay. If this is going to be just standard, ordinary differential equation, then that's going to be 1. So you don't need this one. But now this is going to be multi-dimensional. You got x, y, z. So this is going to be partial derivative. So you need to multiply by x component because this x derivative, nx. Then what about this term? If you again apply integration by part, this take the derivative, and this relieve its derivative. So tau xy, and then dw dy, and then w1 tau xy. But now this is the partial derivative with respect to y. So you got ny component is going to be multiplied by 2 here. Yes.
Where did the n come from?
This is going to be the normal vector. That's the normal vector on the outward direction. So nx and y at the boundary. Okay, you need the magnitude of the normal vector and outward direction positive always. So that's going to be x component and y component of the unit vector, like a cosine and sine of this angle. Okay, so this have to be there because this is going to be partial derivative. That's what we developed in chapter 5. Okay, you can go back to the derivation we have done here. And then likewise, this one, same thing. So change the derivative and the product, but this is also x, so nx. Very consistent. And this is derivative, reverse. So sigma y, no derivative. W2 has derivative. And then this the derivative with respect to y, partial derivative. So you have multiplied by ny in here. Okay, so this is going to be some mathematical aspect, and x and y depends on derivative is going to be x or y. You have to multiply by that one. So if you do that one, then let's look at this one first. This one, this term is same as this term. So this is piece of x. Okay, and this term is equal to this term. So that's the piece of y, right? Piece of x, piece of y. And if this is given, we evaluate. If it's not given, forget about it because we cannot evaluate that one. So that's going to be the traction term. Now, looking at this one, the region, we apply integration by part for that one, which is same as this, one, is that now you can rewrite this in this manner. So stress completely out of derivative. You don't need any derivative. You got sigma x, sigma y, tau of xy. And if you multiply this one, those dw1 dx sigma x, this one, and 0, multiply anything is 0, plus dw1 dy times tau of xy is this one. So that is equal to this product. And the second term, dw2 over dx tau xy. So this one, dw2 dx tau xy, and then dw2 dy, which is this one, times sigma y, and there's no component sigma x, so this is going to be 0. So this is exactly the same as that one. Then what do we do? This is now stress component without derivative. So now we can apply constitutive equation. In other words, this is equal to this. That's what we developed in one of the previous slides. So sigma x, sigma y, tau xy is equal to this matrix, and then epsilon x, epsilon y, gamma sub xy. So in other words, in here, we substitute that constitutive equation. Okay? So that means now this equation contains both equation of equilibrium and constitutive equation. All right? Then what is the last set of equation? Kinematic equation. Kinematic equation is the relationship between strain and displacement. So if you substitute this strain by this kinematic equation, so epsilon x is replaced by du dx, epsilon y is replaced by dv dy, and this engineering shear strain is du dy plus dv dx, replace that. Then now up to here, we consume all the equation. In other words, this equation include equation of equilibrium, constitutive equation, kinematic equation. Everything is included in this expression. Okay, all set of equation. And right-hand side remain the same. Okay, remain the same. So again, this is the domain integral for body force, and that's the bound integral for traction over the surface. So whenever this is given, we are going to carry out this one. But let's focus on this one first. Okay, element matrix. So to evaluate that one, obviously we have to pick the kind of element we are going to analyze. So first of all, the domain is divided into number of finite element domain. Of course, the boundary is going to be divided into number of, the boundary element is there. So let's say I have this kind of 2D domain. This is my 2D domain. And the simplest element, 2D element, is going to be again 3-noded triangular element. That's the simplest one. So we can apply same shape element in here too. Something like that. That's going to be the mesh. Of course, it's not a refined mesh, very crude mesh. So you can mesh like this. Let me complete this one. Excuse me. Like that. So in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. 24 triangular element. I use triangular element. Okay. And also this element could be conventional element or isoparametric element. And most program, 99%, they use isoparametric element because they can write, again, general purpose program for that one. But we are going to learn most of them. So let's think about the traditional element we use. So the triangular element we use in chapter 5, if you remember, 1, 2, 3. So H1, H2, H3, shape function in terms of X and Y. We developed this, right? In chapter 5. So we are going to use that same shape function in here. Okay, we're going to use that one. So if you look at 2D, as is shown in here, how many displacement you have in 2D? the basic displacement is going to be u and v. Displacement in the x direction, displacement in the y direction. So we have a two displacement. So that means I need interpolation of both u and v. U is going to be displacement in the x direction. V is going to be displacement in the y direction. Okay, and this is 3D, then you are going to have a W, and which is going to be displacement along the Z direction. Okay, so but let's focus on 2D. So U and V, XY 2D coordinate system is going to be HI. I is going to be 1, 2, 3 for linear triangular element. Linear triangular element again here. 1, 2, 3. You this project using linear triangular element. So this is going to be x1, y1, x2, y2, and x3, y3 in here. So you develop that one. That means now U and V, now each node has 2 degrees of freedom, not single degree of freedom, 2 degrees of freedom. Then U and V displacement in the element is going to be those two matrix equation is going to be cast into this form of the expression. So in other words, U is going to be H1 times U1 plus 0 plus U2 times H2 times U2 plus 0 plus H3 times U3, which is going to be exactly the same as that one. And then the V is again 0 and H1 times V1 plus H2 times V2 and H3 times V3, so which is going to be same as this one. So in other words, this two set of equation is going to be rewritten in terms of this matrix form, and this we call matrix N. We just defined that. This is going to be matrix N. And this column vector is defined as matrix D, like a displacement vector. So then UV is going to be N times D, matrix N times column vector D. N is going to be this, and D is going to be that. So in here, you have a choice, okay, in arranging this the vector. So this is the choice we prefer. U1, V1, U2, V2, U3, V3. That means, what does it mean? A set of displacement at first node, a set of displacement at second node, a set of displacement at the third node. Okay? But somebody wants to say, well, I prefer, so that I'm going to put this one UV this way. H1, H2, H3, 0, 0, 0. So here U1, U2, U3, and then V1, V2, V3. So I'm going to arrange, this element vector U first and V later. Then that matrix is going to be like this one. Right? This is exactly the same as this one. Just different order. Right? But in general, we prefer this over that. Okay? The reason is this is a little more straightforward than this one in terms of assembled into the global matrix. So this one, the global matrix is going to be like this. U1, V1, U2, V2, U3, V3, U4, V4, and UN, Vn. Always UV, 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 first node to the last node. And then the right-hand side column vector is going to be fx1, fy1, fx2, fy2, fx3, fy3, etc., and then fxn and fyn. So again, xy, 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 xy like that. Okay. So in other words, assembling this into here is a little more preferable than this one. Of course, you can do this one too. Nothing wrong with this one. You know, mathematically this is also correct, but this is more preferable than UV for every node. Okay, and this one, then your column vector instead of that one, your column vector is going to be like this one. If I put it in next in here, it's going to be U1, U2, U3, and UN, and V1, V2, V3, and then Vn like that one. So you got first U and V like the separation, and that's going to be, you know, this the order of matrix is going to be like that one. So again, if you follow everything consistently, you'll get the right answer. Okay, I'm not saying you get the wrong answer because you didn't, you know, put the one way or the other. You'll get the both right answer. But as I said, most program as well as my own program, we prefer this kind of order: UV, UV, UV. So if you have a three-dimensional UVW, then excuse me, U1, V1, W1, U2, V2, W2, U3, V3, W3, like that on, always UVW, UVW like that on. Again, instead of that U, V, and W separately. So those are not preferable in most programs. So anyhow, we write this one in this manner. Okay. If you write this one in this manner, that means this expression du dx, dv dy, and du dy dv dx, we have to carry out derivative, right? So you can carry out derivative here, and you can carry out derivative here. Eventually, same thing. And let's do both, just for you know, clarity of concept. Du dx is summation of I equal 1 to 3, dhi dx and ui, right? Then in here, du dx is, what is that? Th1 dx u1 plus th2 dx u2 plus th3 dx and u sub 3, because it's only 3 of them. And then if you're going to put that in the, again, matrix form, not this explicit equation, but in the matrix form, then you can put this one in this way. Du dx is going to be this one. Again, this t, if I give you explicit information, u1, v1, u2, v2, u3, v3, so that this is only associated this one times u1, and that time u2, and this time u3. So you got 0, 0, 0 for rest of them, because this is only associated u1 and u2, u3 in this manner. Then what about dv dx, dy, dv dy? Dv dy is from here. V dy is summation of I equal 1 to 3, dhi dy vi. So again, this is going to be dh1 dy v1 plus dh2 dy v2 and dh3 dy v sub 3. So which is almost same as that one, except that now this is associated v rather than u. So the same string repeat like that, h1, h2, h3, h1, h2, h3, except that this is going to be derivative x, this derivative y, and then multiply by v1, v2, v3. 2, 4, 6 component, 2, 4, 6. So those are 0, like that. And then last one is that this one. So taking a derivative u respect to y, and taking a derivative v respect to x. So u means that now we are going to take a derivative of this one with respect to y, and v means we are going to take a derivative with respect to y. So if you do that, let's put that on one more time. So d v dy du dy, sorry, plus dv dx is summation I equal 1 to 3 dhi dy and ui plus summation I equal 1 to 3 dhi dx and vi. That's what it means in here. And this is also, if I write it explicitly, plus, now this one is again in explicit sense, h1 dx v1 plus partial h2 dx v2 plus, let me put it in here, partial h3 dx v3, right? So those 6 terms is going to be expressed in this manner. So derivative y, those one, multiplied by u1, u2, u3, and derivative x, this x multiplied by v1, v2, v3. So in other words, this is expressed in this manner. Any questions so far? It looks complicated, but soon you are going to see that this is very obvious, and then you can manipulate this one for not only triangular element, but quadrilateral element, and also extend it to 3D, problem too, without any difficulty. We are going to talk about that a little later, but at least I want to just make sure that now this derivative in terms of the the kinematic equation of the strain displacement relationship, the derivative of displacement is expressed in terms of this matrix and nodal displacement vector t. Okay, so those are the derivative of shape function 1, 2, 3. And we define this is going to be matrix B. We define this as matrix B by definition. We call this one B. So, and this is equal to strain. So strain is equal to B times T. So this is a very common notation. Many books use B in here. So matrix B times nodal displacement T, that's going to be strain component. Okay, so let's take a break here, and then we'll continue from here. Any questions so far? All right, then let's take the break. I need some water too, so. Oops. Stop recording.